Welcome, fellow travelers of the cosmos. Tonight, we embark on a gentle journey through some of the most breathtaking and serene regions of our universe. The nebulae, those magnificent cosmic nurseries where stars are born in clouds of gas and dust that span distances almost beyond imagination. Close your eyes and let your breathing slow naturally. Feel yourself settling into comfort as we prepare to drift through the depths of space, visiting these celestial gardens where light and matter dance together in eternal, peaceful choreography. Before we begin our cosmic voyage, I'm curious, where are you joining us from tonight? Are you perhaps in a cozy bedroom in New York? Or maybe listening from somewhere across the ocean in London? And what time is it where you are? Whether it's late evening or the quiet hours of early morning, you're exactly where you need to be for this tranquil journey through the stars. Chapter 1. The Orion Nebula, our closest star nursery. Let us begin our journey in the constellation of Orion, visible to the naked eye as a fuzzy star in the hunter's sword. The Orion Nebula, also known as Messier 42, lies approximately 1,344 light-years from Earth, a distance so vast that light from this cosmic nursery began its journey to your eyes around the time the Byzantine Empire was flourishing. Imagine yourself gently floating toward this magnificent stellar birthplace. As we approach, the nebula reveals itself not as a single entity, but as a complex tapestry of glowing gas and dark dust lanes, stretching across approximately 24 light-years. To put this in perspective, if you could travel at the speed of light, it would take you 24 years to cross from one side of this nebula to the other. The Orion Nebula glows primarily in shades of red and pink, colors that emerge from hydrogen atoms as they absorb energy from nearby hot, young stars and re-emit it as visible light. This process, called fluorescence, is similar to how a neon sign works, but on a scale that dwarfs our entire solar system. Feel yourself drifting deeper into this cosmic sanctuary. The nebula's central region houses the trapezium cluster, for brilliant young stars that formed only about 1 million years ago, mere infants in cosmic terms. These stellar newborns burn with such intensity that their combined light illuminates the surrounding gas clouds for dozens of light-years in every direction. As you float through the stellar nursery, notice how the gas density varies. In some regions, the hydrogen is so thin that a single cubic centimeter might contain only a few hundred atoms, a vacuum far more complete than anything we can create on Earth. Yet these seemingly empty spaces teem with the raw materials for future stars. The temperature here fluctuates dramatically. While the glowing gas reaches temperatures of 10,000 Kelvin, nearly twice as hot as our sun's surface, the dark dust grains scattered throughout remain frigidly cold, sometimes dropping to just 10 degrees above absolute zero. Watch as invisible magnetic fields thread through the nebular material like cosmic highways, guiding the motion of charged particles and helping to shape the nebula's intricate structure. These magnetic fields, though billions of times weaker than a refrigerator magnet, extend across light-years and play a crucial role in the star formation process. Let your mind rest as we observe the peaceful dance of matter and energy. Shock waves from stellar winds compress the surrounding gas, creating dense pockets where gravity begins to dominate. Over millions of years, these regions will collapse under their own weight, heating up until nuclear fusion ignites and a new star is born. Chapter 2. The Eagle Nebula Pillars of Creation. Our journey continues to one of the most photographed and beloved regions of space. The Eagle Nebula, located 7,000 light-years away in the constellation Serpens. This nebula, designated Messier 16, spans approximately 70 by 55 light-years and serves as both star nursery and cosmic sculptor. As we approach this distant stellar birthplace, you might find yourself wondering about your own location in this vast cosmos. Are you perhaps listening from a quiet room in Tokyo, where the morning sun is just beginning to rise? Or maybe you're in Los Angeles, where the city lights are twinkling below. Whatever time it is in your corner of Earth, allow yourself to float freely through this timeless cosmic landscape. The Eagle Nebula is famous for its towering pillars of creation, enormous columns of cool molecular hydrogen and dust that stretch approximately 4 to 5 light-years in length. These pillars appear as dark silhouettes against the brighter background of the nebula, but they are far from empty. Within their depths, new stars are slowly forming, hidden from view by the very dust that nurtures them. Feel yourself drifting alongside these cosmic monuments. Each pillar is sculpted by the intense stellar winds and radiation from nearby massive stars. Like cosmic sandblasting, this energy gradually erodes the pillars while simultaneously triggering star formation within their dense cores. It's a beautiful paradox. The same forces that destroy these structures also create the conditions necessary for new stellar birth. The Eagle Nebula glows primarily in the red light of hydrogen, but careful observation reveals traces of other elements. Oxygen contributes a blue-green hue, while sulfur adds subtle yellow tones. This cosmic palette results from the different energy levels at which various atoms emit light when excited by stellar radiation. Within the Eagle Nebula's approximately 9,000 solar masses of material, astronomers have identified numerous sites of active star formation. Some of these stellar embryos are still deeply embedded in their dusty cocoons, detectable only by the infrared heat they generate as they slowly contract under gravity's influence. The process of star formation here is remarkably patient. While we humans measure significant events in years or decades, the Eagle Nebula operates on timescales of millions of years. A star's birth is a gradual awakening. As a cold clump of gas and dust slowly collapses, spins faster, heats up, and eventually ignites the nuclear fires that will sustain it for billions of years. Imagine the serenity of this process. There are no explosions, no sudden violence, just the slow, inevitable dance of gravity and matter. Dense cores within the pillars contract at a rate of perhaps a few kilometers per year, imperceptible on human timescales but inexorable over cosmic time. As you float through the stellar nursery, notice how the nebulous structure reveals the history of star formation in this region. The central cavity, where we now find young, hot stars, was once filled with the same dense material that now forms the outer pillars. Over time, stellar winds and radiation have carved out this space, creating a bubble in the interstellar medium. The temperature variations throughout the Eagle Nebula create a complex ecosystem of stellar birth. The hottest regions, heated by young stars to tens of thousands of degrees, exist alongside cold molecular clouds where temperatures hover just a few degrees above absolute zero. This temperature gradient drives the complex chemistry necessary for star formation. Chapter 3. The Orion Nebula, a cosmic tempest of creation. Our gentle voyage now carries us to the southern hemisphere's crown jewel, the Orion Nebula, designated NGC 3372. Located approximately 7,500 light-years from Earth, this massive star-forming region spans over 300 light-years across, making it one of the largest and most active stellar nurseries in our local region of the galaxy. Before we immerse ourselves in this cosmic wonderland, take a moment to consider your own place in the universe. Perhaps you're listening from a peaceful bedroom in Sydney, where the Southern Cross shines overhead, or maybe from a cozy apartment in Sao Paulo, where the night is deep and quiet. Wherever you are, and whatever time your clock displays, you're part of this same cosmic story unfolding around us. The Orion Nebula is home to some of the most massive and luminous stars known to astronomy. At its heart lies Eta Carinae, a hypergiant star system that experienced a spectacular eruption in the 1840s, briefly becoming the second brightest star in Earth's sky. This stellar giant, with a mass perhaps 150 times that of our Sun, continues to fascinate astronomers as it sheds material at an extraordinary rate. As we drift through this cosmic maelstrom, notice how the nebula's structure reflects the violent yet beautiful life cycles of its most massive inhabitants. The nebula glows intensely in hydrogen's characteristic red light, but the presence of numerous hot, young stars creates a complex tapestry of colors. Blue and violet regions mark areas where the hottest stars ionize surrounding gas, while cooler regions glow in softer reds and oranges. The Carina Nebula contains approximately 1 million solar masses of material, enough raw material to form hundreds of thousands of sun-like stars. This vast reservoir of hydrogen, helium, and heavier elements represents the recycled remnants of previous generations of stars, enriched with the products of stellar nucleosynthesis and distributed by ancient supernova explosions. Feel yourself floating through the nebula's intricate network of cavities and pillars. Like the Eagle Nebula, the Carina Nebula has been sculpted by stellar winds and radiation pressure from its massive inhabitant stars. These forces have excavated enormous bubbles in the interstellar medium, creating a complex three-dimensional structure that extends far beyond what we can see in two-dimensional images. The star formation process in the Carina Nebula operates on multiple scales simultaneously. While individual stellar nurseries might span only a few light-years, the entire nebular complex represents a vast stellar manufacturing facility that has been producing stars for millions of years. The most massive stars, burning their nuclear fuel at prodigious rates, live fast and die young, their brief but brilliant lives triggering the formation of subsequent generations of stars. Temperature gradients throughout the nebula create distinct zones of stellar birth. The hottest regions, where massive stars have cleared away most of the surrounding material, reach temperatures of 50,000 Kelvin or more. Meanwhile, dense molecular clouds within the nebula remain cold and dark, their temperatures hovering near 10 Kelvin, perfect conditions for the slow gravitational collapse that leads to star formation. One of the most remarkable features of the Carina Nebula is its collection of stellar nurseries known as globules. These dark, dense clouds appear as silhouettes against the bright nebular background, but within their opaque interiors, new stars are taking their first tentative steps toward nuclear ignition. Some of these globules are being actively eroded by nearby stellar radiation, creating comet-like structures with bright rims and dark tails. The nebula's magnetic field plays a crucial role in organizing star formation across this vast region. Invisible to our eyes but detectable through its effects on charged particles and dust grains, the magnetic field creates preferred directions for material flow and helps determine where new stars will form. These cosmic magnetic highways extend across dozens of light-years, connecting distant regions of the nebula in a complex web of electromagnetic influence. As you continue your peaceful drift through the Carina Nebula, observe how different regions exhibit varying stages of stellar evolution. Young, embedded protostars heat their surrounding dust cocoons, creating warm regions detectable in infrared light. Slightly older stars have begun to emerge from their birth material, their stellar winds starting to clear away the gas and dust that once surrounded them. The oldest stars in the region have created vast cavities around themselves, their intense radiation ionizing material across dozens of light-years. Chapter 4. The Helix Nebula, the Eye of the Cosmos. Our serene journey through the universe's stellar nurseries now brings us to a different type of nebula, one that represents not birth, but transformation. The Helix Nebula, often called the Eye of God or the Eye of the Cosmos, lies approximately 650 light-years away in the constellation Aquarius. This is not a star-forming region, but rather a planetary nebula, the final act in the life of a sun-like star. As we approach this cosmic eye, I wonder about your own observations of the night sky. Are you perhaps viewing from a location where the constellation Aquarius is visible overhead? Maybe from a balcony in Cairo where the desert air is crystal clear? Or are you in Vancouver, where city lights might make the stars harder to see, but where your imagination can carry you just as far into the depths of space? The Helix Nebula spans approximately 2.5 light-years across roughly 15 trillion miles, making it one of the largest and closest planetary nebulae to Earth. Despite its name, planetary nebulae have nothing to do with planets. They received this designation from early astronomers who thought their round, disc-like appearance resembled planets when viewed through small telescopes. At the center of this cosmic eye sits a white dwarf star, the collapsed core of what was once a star similar to our Sun. This stellar remnant, no larger than Earth but containing about 60% of our Sun's mass, represents the final fate awaiting our own star in approximately 5 billion years. The white dwarf's surface temperature reaches about 120,000 Kelvin, 10 times hotter than our Sun, and its intense ultraviolet radiation ionizes the surrounding shell of gas that was expelled during the star's final phases. Feel yourself drifting into the heart of this cosmic eye. The nebula's distinctive braided structure results from complex interactions between the expelled stellar material and the intense stellar winds from the central white dwarf. These processes have created intricate knots and filaments throughout the nebula, each one a testament to the turbulent final years of the original star's life. The Helix Nebula glows in multiple colors, each representing different elements being excited by the central star's radiation. Hydrogen produces the familiar red glow, while doubly ionized oxygen creates blue-green regions. Nitrogen contributes red hues that blend with hydrogen's emission, while helium adds yellow and green tones to the cosmic palette. The nebula's expansion velocity provides clues about its age and formation history. Moving outward at approximately 31 kilometers per second, the gas shell has been expanding for roughly 10,600 years, a relatively recent event in cosmic terms. This means that when humans were developing agriculture and founding the first cities, this star was undergoing its transformation from red giant to white dwarf. Within the Helix Nebula's glowing gas, astronomers have discovered thousands of comet-like knots, each roughly the size of our solar system. These dense condensations of material, sculpted by the central star's radiation, appear to be the remnants of the original star's outer atmosphere. Some of these knots show evidence of complex chemistry, including the formation of simple molecules despite the harsh radiation environment. The white dwarf at the nebula's center will continue to slowly cool over billions of years, gradually fading from white-hot to yellow, then red, and eventually becoming a cold, dark stellar remnant known as a black dwarf. However, the universe is not yet old enough for any white dwarfs to have completed this cooling process. Every white dwarf that has ever formed is still glowing with the heat of its formation. As you float through this cosmic memorial to a sun-like star, consider the peaceful nature of this stellar death. Unlike the violent explosions that mark the end of massive stars, the formation of planetary nebulae is a gradual, almost gentle process. The dying star slowly puffs off its outer layers over thousands of years, creating these beautiful, expanding shells of ionized gas. The Helix Nebula serves as a preview of our own solar system's distant future. In about 5 billion years, our Sun will undergo a similar transformation, swelling into a red giant before expelling its outer layers to create a planetary nebula. The Earth, if it survives the Sun's red giant phase, will be bathed in the light of our Sun's own cosmic eye. Chapter 5. The Rosette Nebula, a stellar garden in bloom. Our tranquil voyage continues to the Rosette Nebula, also known as NGC 2237, located approximately 5,200 light-years away in the constellation Nurseries. This beautiful emission nebula resembles a cosmic rose in bloom, its petals formed by the complex interplay between stellar winds, radiation pressure, and the surrounding interstellar medium. Before we explore this celestial garden, let me ask, Where has your evening taken you? Perhaps you're nestled in a comfortable chair in Stockholm, where the long winter night provides perfect darkness for contemplating the cosmos. Or maybe you're in Mumbai, where the busy day is winding down and the stars are beginning to emerge through the urban glow. Whatever your location and whatever hour your timepiece shows, you're invited to lose yourself in the timeless beauty of stellar birth. The Rosette Nebula spans approximately 100 light-years in diameter and contains enough material to form more than 10,000 sun-like stars. At its heart lies the NGC 2244 cluster, a group of hot, young stars that formed from the nebula's material roughly 4 million years ago. These stellar children have now grown powerful enough to sculpt their birth environment, their combined stellar winds and radiation creating the central cavity that gives the nebula its distinctive rose-like appearance. As we drift into this cosmic flower, notice how the nebula's structure reveals the ongoing battle between stellar energy and gravitational collapse. The hot central stars have blown a bubble in the surrounding material, but gravity continues to work on the remaining gas and dust, creating dense pillar-like structures along the nebula's rim where new generations of stars are taking shape. The Rosette Nebula glows primarily in the red light of hydrogen alpha emission, creating the warm, rose-colored hue that gives the nebula its name. However, careful observation reveals subtle variations in color throughout the structure. Regions of doubly ionized oxygen contribute blue-green tones, while areas rich in sulfur add yellow hues to the cosmic palette. Feel yourself floating through the nebula's intricate network of gas and dust. The density variations you encounter range from nearly perfect vacuum in the central cavity to regions where each cubic centimeter contains millions of atoms, still incredibly thin by terrestrial standards, but dense enough for gravity to begin gathering material into future stars. The temperature structure of the Rosette Nebula creates distinct zones of stellar activity. The central cavity, heated by the young star cluster, maintains temperatures around 10,000 Kelvin. However, the dense molecular clouds along the nebula's periphery remain cold, with temperatures dropping to just 10 to 20 Kelvin above absolute zero. These frigid regions provide the perfect conditions for molecules to form and for gravity to slowly compress material into stellar nurseries. Stellar winds from the central cluster travel at velocities exceeding 2,000 kilometers per second, carrying energy and momentum far into the surrounding medium. These winds have sculpted the nebula over millions of years, creating a complex system of shocks, compressions, and expansions that continue to influence star formation throughout the region. The Rosette Nebula contains several distinct sites of active star formation, visible as dark globules silhouetted against the bright background emission. These elephant trunk structures point toward the central cavity, sculpted by the pressure of stellar radiation and winds. Within these dense pillars, astronomers have identified numerous young stellar objects, protostars in various stages of formation. Magnetic fields thread through the Rosette Nebula's structure, invisible to the naked eye but detectable through their influence on charged particles and dust grains. These cosmic magnetic highways help channel material flow during star formation and play a crucial role in determining the final masses and characteristics of newly forming stars. As you continue your peaceful journey through this stellar garden, observe how the nebula represents a snapshot of ongoing cosmic evolution. The central stars, though only a few million years old, have already begun to transform their environment. In another few million years, their stellar winds will have dispersed much of the remaining nebular material, leaving behind an open star cluster embedded in a much more tenuous medium. The Rosette Nebula's beauty extends far beyond visible light. In infrared wavelengths, the nebula reveals warm dust heated by stellar radiation, creating intricate patterns invisible to our eyes. Radio observations detect the emission from carbon monoxide and other molecules, mapping the cold, dense regions where star formation continues. Each wavelength of light tells a different part of the nebula's story, revealing layers of complexity hidden from casual observation. Chapter 6. The Horsehead Nebula Silhouette of Stellar Birth. Our gentle drift through the cosmos now carries us to one of the most recognizable and beloved features of the night sky, the Horsehead Nebula, known formally as Barnard 33. Located approximately 1,500 light-years away in the constellation Orion, this dark nebula appears as a striking silhouette against the bright background of the emission nebula IC 434. As we approach this cosmic sculpture, I'm curious about your own relationship with the night sky. Are you perhaps observing from a location with particularly dark skies? Maybe a cabin in the Rocky Mountains where the Milky Way stretches brilliantly overhead? Or are you in a bustling city like London or New York, where the glow of human activity has hidden most stars, but where your imagination can still carry you to the darkest regions of space? And what time has your journey brought you to? Are you settling into sleep as midnight approaches, or are you greeting the dawn hours with cosmic contemplation? The Horsehead Nebula represents a different type of stellar nursery, a dark nebula, where dense clouds of dust and gas block the light from more distant stars and glowing gas. This dark cloud, measuring approximately 3.5 light-years from top to bottom, contains enough material to form several dozen sun-like stars. However, the density here is still incredibly low by terrestrial standards. Even the densest regions contain only about 10,000 atoms per cubic centimeter, compared to the 25 billion trillion atoms in each cubic centimeter of air at sea level. Feel yourself drifting into this cosmic shadow. The Horsehead's distinctive shape results from the complex interplay between stellar radiation from nearby hot stars and the varying density of the dark cloud itself. The Horse's head profile is sculpted by radiation pressure and stellar winds from Sigma Orionis, a multiple star system located just outside the field of view. This stellar energy gradually erodes the dark cloud, revealing the characteristic equine silhouette that has captured human imagination for generations. Within the Horsehead Nebula, temperatures drop to approximately 10 to 20 Kelvin, just a few degrees above absolute zero. These frigid conditions allow molecules to form and survive, creating a rich chemistry invisible to optical telescopes but detectable through radio and millimeter wave observations. Carbon monoxide, formaldehyde, methanol, and dozens of other molecules paint a complex chemical portrait of this stellar nursery. The nebula's magnetic field plays a crucial role in its structure and evolution. These invisible force lines help support the cloud against gravitational collapse while also channeling the flow of ionized material. The magnetic field strength in the Horsehead is roughly comparable to Earth's magnetic field, but extended across light-years rather than thousands of kilometers. As you float through this dark cosmic landscape, notice how the absence of light creates its own form of beauty. The Horsehead Nebula appears dark not because it lacks material, but because it contains so much dust that it blocks the light from stars and glowing gas behind it. This dust, composed of tiny particles of carbon, silicon, and other heavy elements, was forged in the nuclear furnaces of previous generations of stars and distributed through space by stellar winds and supernova explosions. The Horsehead Nebula is slowly being eroded by radiation from nearby stars, losing approximately 1 Earth mass of material every million years. At this rate, the nebula's distinctive shape will survive for roughly another 5 million years before being completely dispersed. This ongoing erosion process creates a dynamic boundary layer where the dark cloud meets the bright emission nebula, generating complex shock structures and compression waves that may trigger star formation in the dense molecular material. Despite its appearance as a static silhouette, the Horsehead Nebula harbors active star formation deep within its dusty interior. Infrared observations have revealed several young stellar objects embedded in the cloud, their warm radiation detectable despite being completely obscured at visible wavelengths. These stellar embryos represent the future of this region, Eventually, they will emerge from their dusty cocoons as newly minted stars, their radiation joining the cosmic forces that continue to sculpt the interstellar medium. The chemical complexity within the Horsehead Nebula extends far beyond simple molecules. Astronomers have detected organic compounds including ethyl alcohol, acetone, and even amino acid precursors within similar dark clouds. These discoveries suggest that the basic chemical building blocks of life may be common throughout the universe, forming naturally in the cold, dense environments where stars are born. As you continue your tranquil journey through this cosmic shadow, consider the Horsehead Nebula's role in the greater story of stellar evolution. Dark nebulae like this one represent the raw material reservoirs from which new stars form. The dust and gas that currently block our view of distant stars will eventually collapse under gravity's influence, heat up, and ignite nuclear fusion. In this way, today's dark nebulae become tomorrow's bright star-forming regions, continuing the eternal cycle of stellar birth, life, and death that has shaped our galaxy for billions of years. Chapter 7. The Cat's Eye Nebula, Cosmic Complexity Unveiled. Our peaceful voyage through the universe's stellar nurseries now brings us to another planetary nebula. The Cat's Eye Nebula, designated NGC 6543, located approximately 3,300 light-years away in the constellation Draco. Like the Helix Nebula we visited earlier, this remarkable structure represents the final phase in the life of a sun-like star, but with a complexity that continues to puzzle and delight astronomers. Before we immerse ourselves in this cosmic enigma, take a moment to consider your own place in this vast universe. Perhaps you're listening from a peaceful bedroom in Tokyo, where the city never truly sleeps but the night offers a respite from the day's activities. Or maybe you're in a quiet cottage in the Scottish Highlands, where the darkness is profound and the stars shine with exceptional clarity. Whatever corner of our planet you call home tonight, and whatever hour the clock displays, you're part of the same cosmic story that created the elements in your body and the ground beneath your feet. The Cat's Eye Nebula spans approximately half a light-year across, about 30,000 times the distance from Earth to the Sun, and displays one of the most complex structures ever observed in a planetary nebula. At its center lies a white dwarf star with a surface temperature exceeding 80,000 Kelvin, making it one of the hottest white dwarfs known. This stellar remnant ionizes the surrounding gas with its intense ultraviolet radiation, creating the nebula's characteristic multicolored glow. As we approach this cosmic eye, notice how the nebula's structure defies simple explanation. Unlike the relatively smooth shells we might expect from a single star's death, the Cat's Eye displays multiple concentric shells, symmetrical jets, and intricate knots of material. This complexity suggests that the original star experienced multiple episodes of mass loss, possibly indicating the presence of a binary companion that influenced the dying star's behavior. Feel yourself drifting into the heart of this celestial complexity. The nebula's central region glows brilliantly in the green light of doubly ionized oxygen, creating the eye that gives the nebula its name. Surrounding this central region, concentric shells of material expand outward at different velocities, some moving at 10 kilometers per second, while others race outward at speeds exceeding 50 kilometers per second. The Cat's Eye Nebula's color palette tells the story of its elemental composition. The bright green core results from oxygen atoms that have lost 2 electrons, excited by the central white dwarf's intense radiation. Red regions indicate hydrogen emission, while blue areas show the presence of helium and other highly ionized elements. Yellow and orange hues result from the combination of multiple emission lines, creating a cosmic stained glass window of unprecedented beauty. Temperature variations throughout the nebula create distinct ionization zones. The region closest to the central white dwarf reaches temperatures of 15,000 Kelvin, hot enough to strip multiple electrons from oxygen and nitrogen atoms. Further from the center, temperatures drop to around 8,000 Kelvin, where hydrogen can recombine with electrons and emit its characteristic red light. One of the most intriguing features of the Cat's Eye Nebula is its system of symmetrical jets extending far beyond the main nebular structure. These jets, visible only in deep images, stretch across several arc-minutes of sky and appear to precess like cosmic spinning tops. The mechanism responsible for creating these jets remains a subject of active research, with theories ranging from magnetic field interactions to the influence of an unseen binary companion. The nebula's intricate knot structure provides clues about the final stages of stellar evolution. Some knots appear to be dense condensations of material ejected during specific episodes of mass loss, while others may result from instabilities in the expanding gas shell. Each knot represents a small-scale laboratory where astronomers can study the physics of ionized gas under extreme conditions. As you float through this cosmic complexity, observe how the Cat's Eye Nebula challenges our understanding of stellar death. The multiple shells and symmetrical structures suggest that the dying star experienced a series of thermal pulses, periodic instabilities that caused it to eject material in discrete episodes over thousands of years. These pulses may have been triggered by helium flash events in the star's interior, creating the layered structure we observe today. The chemical composition of the Cat's Eye Nebula reveals the nuclear history of its progenitor star. Nitrogen, created through hydrogen burning in the star's core, appears enhanced compared to typical interstellar abundances. Carbon, produced during helium burning phases, also shows elevated levels. These abundance patterns provide a forensic record of the nuclear processes that powered the original star throughout its lifetime. Magnetic fields play a crucial role in shaping the Cat's Eye Nebula's structure. The central white dwarf maintains a magnetic field roughly 1,000 times stronger than Earth's, capable of channeling ionized material into the observed jet structures. These magnetic effects, combined with stellar rotation and possible binary interactions, create the complex symmetries that make this nebula so visually striking. The Cat's Eye Nebula continues to evolve before our eyes, though the changes occur over decades rather than human lifetimes. Comparison of images taken years apart reveals subtle shifts in the positions of knots and filaments, allowing astronomers to measure the nebula's expansion velocity and trace the history of mass ejection events. These observations provide crucial insights into the final phases of stellar evolution and help refine our understanding of how sun-like stars end their lives. Chapter 8. The Lagoon Nebula, a cosmic lagoon of stars. Our serene journey through the universe's stellar birthplaces now carries us to the Lagoon Nebula, designated Messier 8, located approximately 4,100 light-years away in the constellation Sagittarius. This magnificent emission nebula serves as one of the most accessible stellar nurseries for observers in the Northern Hemisphere, visible to the naked eye as a cloud-like patch in the rich star fields toward the galactic center. As we approach this cosmic lagoon, I find myself wondering about your own connection to the night sky. Are you perhaps observing from somewhere with an excellent view of the summer Milky Way? Maybe a campsite in the Canadian wilderness where the galactic plane stretches from horizon to horizon? Or are you in a city like Barcelona or San Francisco, where the urban glow dims the stars but your imagination can still transport you to the darkest corners of space? And as we drift together through this stellar nursery, what time marks your own journey through this night? Are you settling into the peaceful hours before dawn? Or are you beginning your cosmic exploration as evening deepens around you? The Lagoon Nebula spans approximately 110 by 50 light-years, making it one of the largest and brightest emission nebulae visible from Earth. The nebula contains roughly 1,000 times the mass of our Sun in gas and dust, providing abundant raw material for ongoing star formation. At the nebula's heart lies the Hourglass Nebula, a smaller, more intense region where hot, young stars have carved out a distinctive cavity in the surrounding material. Feel yourself drifting into this cosmic oasis. The nebula's distinctive lagoon appearance results from a dark lane of obscuring dust that bisects the brighter emission regions. This dark lane, composed of tiny particles of carbon and silicate dust, blocks the light from the nebula's far side while allowing us to peer into the three-dimensional structure of this stellar nursery. The Lagoon Nebula glows primarily in the red light of hydrogen alpha emission, created when hydrogen atoms absorb ultraviolet photons from nearby hot stars and re-emit the energy as visible light. The nebula's ionization is powered by several massive O-type stars, including Herschel 36, a multiple star system with combined luminosity nearly 200,000 times that of our Sun. These stellar powerhouses burn their nuclear fuel at such prodigious rates that they will live only a few million years before ending their lives in spectacular supernova explosions. Temperature gradients throughout the Lagoon Nebula create distinct zones of stellar activity. Near the hot ionizing stars, gas temperatures reach 8,000 to 10,000 Kelvin, hot enough to keep hydrogen completely ionized. Further from these stellar furnaces, temperatures drop to a few hundred Kelvin, allowing molecules to form and survive. These cooler regions appear as dark patches and globules where future generations of stars will form. The nebula's magnetic field structure influences both its appearance and its star formation activity. Invisible magnetic force lines thread through the ionized gas, channeling the flow of charged particles and helping to organize the nebula's filamentary structure. These magnetic fields, though incredibly weak by terrestrial standards, extend across dozens of light years and play a crucial role in the star formation process. As you float through this cosmic lagoon, observe how stellar winds from the central massive stars have sculpted the surrounding material into intricate patterns. The Hourglass Nebula at the lagoon's center represents one of the most active star-forming regions in our local galactic neighborhood. Here, stellar winds traveling at thousands of kilometers per second collide with dense molecular material, creating shock waves that compress the gas and trigger the collapse of nearby stellar nurseries. The Lagoon Nebula hosts numerous sites of active star formation, many invisible to optical telescopes but detectable in infrared light. These embedded protostars heat their surrounding dust cocoons to temperatures of a few hundred Kelvin, causing them to glow in wavelengths beyond human vision. Some of these stellar embryos will eventually become massive stars themselves, continuing the cycle of stellar birth and death that has shaped this region for millions of years. Within the nebula's complex structure, astronomers have identified several distinct types of stellar nurseries. Bright-rimmed clouds appear as glowing edges around dark molecular cores, illuminated by radiation from nearby hot stars. These structures often show evidence of triggered star formation, where the pressure from stellar radiation compresses the dense material enough to initiate gravitational collapse. The chemical composition of the Lagoon Nebula reflects both its stellar population and its evolutionary history. Enhanced nitrogen abundances in certain regions suggest contamination from stellar winds from evolved massive stars. The presence of complex molecules, including water vapor and methanol, indicates that despite the harsh radiation environment, chemistry continues to operate in the nebula's cooler, denser regions. Chapter 9. The Trifid Nebula, a tricolor cosmic rose. Our peaceful cosmic voyage continues to the nearby Trifid Nebula, designated Messier 20, located just 1.5 degrees from the Lagoon Nebula in the constellation Sagittarius. This spectacular object, situated approximately 5,200 light-years from Earth, combines both emission and reflection nebulae in a single, breathtaking structure that has earned it the nickname the Tricolor Nebula. Before we explore this cosmic masterpiece, I'm curious about your own experience of color in the night sky. Are you perhaps observing from a location where light pollution has washed out the subtle hues of celestial objects? Maybe from an apartment in Paris or Chicago, where only the brightest stars penetrate the urban glow? Or are you blessed with dark skies in a place like rural Montana or the Australian outback, where even faint nebulae reveal their colors to patient observers? Whatever your vantage point on Earth, and whatever hour your clock displays, the cosmos invites you to imagine the full spectrum of colors that paint these distant stellar nurseries. The Trifid Nebula spans approximately 40 light-years across and contains roughly 3,000 solar masses of material. Its distinctive appearance results from the combination of three different types of cosmic phenomena. The central region glows red with hydrogen emission, powered by a single O-type star designated HD 164492. This stellar giant, with a surface temperature exceeding 40,000 Kelvin, ionizes hydrogen across dozens of light-years, creating the nebula's warm, rose-colored glow. Feel yourself drifting into this tricolor cosmic garden. The nebula's most striking feature consists of three dark dust lanes that intersect near its center, creating the Trifid appearance that gives the nebula its name. These dark lanes, composed of microscopic dust particles that efficiently absorb and scatter starlight, reveal the three-dimensional structure of the stellar nursery by silhouetting denser regions against the bright background emission. To the north of the emission region lies a blue reflection nebula, where starlight from nearby hot stars scatters off dust particles in the surrounding medium. This scattering process, similar to the mechanism that makes Earth's sky blue, preferentially reflects shorter wavelength blue light while allowing longer wavelength red light to pass through unimpeded. The result is a beautiful blue glow that contrasts dramatically with the red emission regions. The Trifid Nebula's young stellar population provides insights into the earliest stages of massive star formation. The central ionizing star, estimated to be only 300,000 years old, represents one of the youngest known O-type stars. Its extreme youth is evidenced by its location at the center of the nebular cavity it has created. Older massive stars would have had time to move away from their birth sites due to their peculiar space velocities. Temperature variations throughout the Trifid create distinct ecological zones for different types of stellar birth. The hot ionized region maintains temperatures around 8,000 Kelvin, while the reflection nebula regions remain much cooler at a few hundred Kelvin. The dark dust lanes that define the nebula's structure harbor the coldest material, with temperatures dropping to just 10 to 20 Kelvin above absolute zero. As you float through this cosmic intersection of light and shadow, observe how the Trifid Nebula demonstrates the complex feedback between massive stars and their birth environments. The central O-type star has not only ionized the surrounding hydrogen, but also compressed nearby molecular material through its intense stellar winds. This compression has triggered secondary star formation in several locations around the nebula's periphery. The nebula's magnetic field structure plays a crucial role in organizing its appearance and evolution. Magnetic force lines, invisible to optical telescopes but detectable through polarization measurements, help channel the flow of ionized material and influence the formation of the prominent dust lanes. These magnetic highways extend throughout the nebular complex, connecting regions separated by multiple light-years. Within the Trifid Nebula's structure, astronomers have identified numerous examples of triggered star formation. Dense molecular clumps along the nebula's boundaries show signs of ongoing collapse, compressed by the expanding ionization front driven by the central massive star. Some of these regions contain embedded infrared sources, young protostars that will eventually emerge as the next generation of stellar inhabitants. The chemical environment within the Trifid reflects the ongoing interplay between stellar nucleosynthesis and interstellar chemistry. The central regions, enriched by stellar winds from the massive ionizing star, show enhanced abundances of nitrogen and other products of stellar hydrogen burning. Meanwhile, the cooler outer regions preserve a more primitive chemical composition, closer to that of the original molecular cloud from which the nebula formed. The Trifid Nebula's relatively small angular size and moderate distance make it an ideal laboratory for studying star formation processes. The entire stellar nursery can be observed with single telescope pointings, allowing astronomers to trace the connections between different regions and understand how star formation propagates through molecular cloud complexes. Chapter 10. The Veil Nebula Remnants of Stellar Catastrophe. Our gentle journey through cosmic nurseries now brings us to a different type of nebula entirely, the Veil Nebula, also known as the Cygnus Loop, located approximately 2,100 light-years away in the constellation Cygnus. Unlike the star-forming regions we've explored, this magnificent structure represents the aftermath of stellar death, a supernova remnant that showcases the violent yet beautiful end of a massive star's life. As we approach this cosmic tapestry, I wonder about your own relationship with cycles of creation and destruction. Are you perhaps listening from a quiet room in Seattle, where the autumn rain creates its own gentle rhythm outside your window? Or maybe you're in a peaceful spot in rural Japan, where the changing seasons remind us of nature's eternal cycles. Whatever your location on our small planet, and whatever time your evening or early morning has brought you to, consider how even destruction in the cosmos leads to new possibilities for creation. The Veil Nebula spans approximately 3 degrees across the sky, 6 times the apparent diameter of the full moon, and extends roughly 110 light-years from end to end. This enormous structure represents the expanding shock wave from a supernova explosion that occurred approximately 8,000 years ago, when early human civilizations were just beginning to develop agriculture and build permanent settlements. Feel yourself drifting into this cosmic memorial to stellar violence. The original star that created this magnificent structure was likely 15 to 20 times more massive than our Sun. After burning through its nuclear fuel in just a few million years, the star's core collapsed catastrophically, releasing more energy in a few seconds than our Sun will produce over its entire 10-billion-year lifetime. The explosion hurled the star's outer layers into space at velocities exceeding 1,000 kilometers per second. The Veil Nebula's intricate filamentary structure results from the complex physics of shock wave propagation through the heterogeneous interstellar medium. As the supernova blast wave encounters regions of varying density, it creates a network of glowing filaments where compressed gas radiates energy across the electromagnetic spectrum. These filaments, some extending across multiple light-years, trace the boundaries between the hot, shocked material and the cooler ambient interstellar gas. The nebula's beautiful colors tell the story of different physical processes occurring within the shock-heated gas. Red regions indicate hydrogen emission from areas where the shock wave has heated gas to approximately 10,000 Kelvin. Blue-green areas show the characteristic glow of doubly ionized oxygen, requiring higher temperatures and more energetic shocks. The finest filamentary structures often appear white or blue, indicating regions where the shock is still actively propagating through dense material. Temperature gradients throughout the Veil Nebula create a complex thermal landscape. The hottest regions, where the shock wave is most active, reach temperatures exceeding 1 million Kelvin, hot enough to emit X-rays detectable by space-based telescopes. However, the optical filaments we observe represent much cooler material, typically around 20,000 Kelvin, where the shock has begun to slow and the gas has had time to cool through radiation. As you drift through this cosmic shockwave, observe how the Veil Nebula enriches the interstellar medium with heavy elements forged in the original star's nuclear furnace. The explosion has distributed iron, nickel, cobalt, and dozens of other elements across hundreds of cubic light-years of space. These materials, essential for the formation of rocky planets and the development of life, now permeate the local interstellar environment and will eventually be incorporated into future generations of stars. The supernova remnant continues to evolve thousands of years after the initial explosion. The expanding shock wave has now slowed considerably as it encounters increasing amounts of interstellar material. Currently moving at approximately 200 kilometers per second, the shock will continue to expand for hundreds of thousands of years before eventually merging with the general turbulence of the interstellar medium. Within the Veil Nebula structure, astronomers have identified regions where the supernova shock wave is triggering new episodes of star formation. Dense molecular clouds encountered by the expanding blast wave become compressed, potentially initiating gravitational collapse in material that might otherwise remain stable against star formation. In this way, stellar death leads directly to stellar birth, continuing the cosmic cycle that has operated throughout our galaxy's history. The magnetic field structure within the Veil Nebula provides insights into the physics of shock wave propagation and particle acceleration. The supernova explosion has amplified and tangled the local magnetic field, creating conditions conducive to accelerating charged particles to extremely high energies. Some of these particles may eventually reach Earth as cosmic rays, carrying information about stellar death across the galaxy. The chemical composition of different regions within the Veil Nebula reflects both the nucleosynthetic products of the original massive star and the composition of the interstellar material being swept up by the shock wave. Enhanced abundances of elements like oxygen, neon, and magnesium in certain filaments indicate material that originated in the star's interior, while other regions show compositions more typical of unprocessed interstellar gas. Chapter 11. The North American Nebula, a continental cloud of stars. Our peaceful cosmic voyage now carries us to the North American Nebula, designated NGC 7000, located approximately 2,600 light-years away in the constellation Cygnus. This large emission nebula, covering an area of sky roughly 4 times the size of the full moon, derives its name from its striking resemblance to the North American continent when viewed in hydrogen alpha light. Before we explore this continental stellar nursery, let me ask about your own continental perspective. Are you perhaps observing from somewhere on the actual North American continent? Maybe from a cozy cabin in the Canadian Rockies where the constellation Cygnus soars high overhead? Or are you viewing from another continent entirely, perhaps from a peaceful location in New Zealand where the southern sky offers its own treasures? Or from somewhere in Europe where ancient stone circles once marked humanity's first attempts to understand the cosmos? Whatever continent you call home tonight, and whatever hour marks your personal journey through this evening, you're invited to explore this cosmic continent floating in the depths of space. The North American Nebula spans approximately 100 light-years across and contains roughly 4,000 solar masses of material, enough raw material to form thousands of sun-like stars. The nebula's distinctive continental shape results from the complex interplay between ionizing radiation from hot, young stars and the varying density structure of the surrounding molecular cloud. A prominent dark lane, corresponding to the Gulf of Mexico in the nebula's geographic analogy, consists of dense dust that obscures the light from more distant parts of the nebular complex. Feel yourself drifting across this cosmic continent. The nebula's ionization is powered primarily by a single hot star, possibly a Wolf-Rayet star or an O-type giant, hidden behind the dense dust lane that creates the Gulf of Mexico feature. This unseen stellar powerhouse pumps out enormous quantities of ultraviolet radiation, ionizing hydrogen atoms across dozens of light-years and causing the nebula to glow in its characteristic red hue. The North American Nebula represents part of a much larger molecular cloud complex that includes the nearby Pelican Nebula. Together, these structures trace the boundaries of an enormous stellar nursery where star formation has been ongoing for millions of years. The Atlantic Ocean region to the east of the main nebular structure contains numerous dark globules, dense molecular cores where the next generation of stars is slowly taking shape. Temperature variations across this cosmic continent create distinct zones of stellar activity. The bright emission regions, heated by the central ionizing source, maintain temperatures around 8,000 Kelvin. However, the dark dust lanes and molecular cores remain much cooler, with temperatures dropping to just 10 to 20 Kelvin above absolute zero. These frigid regions provide ideal conditions for molecule formation and the slow gravitational collapse that leads to star birth. The nebula's Pacific coast corresponds to a sharp ionization boundary where the stellar radiation encounters a dense wall of molecular material. This interface, known as a photodissociation region, hosts complex chemistry as ultraviolet photons break apart molecules while simultaneously providing the energy for new chemical reactions. The resulting environment produces a rich array of interstellar molecules, from simple carbon monoxide to complex organic compounds. As you float across the stellar continent, observe how the North America Nebula demonstrates the hierarchical nature of star formation. While the large-scale structure is shaped by a single massive ionizing star, smaller-scale star formation occurs throughout the complex in dense molecular cores. Some of these cores show evidence of active collapse, detectable through their infrared emission as embedded protostars heat their surrounding dust cocoons. The magnetic field structure within the North America Nebula plays a crucial role in organizing both its appearance and its star formation activity. Invisible magnetic force lines thread through the ionized gas, channeling the flow of charged particles and helping to maintain the sharp boundaries between ionized and neutral regions. These magnetic fields also influence the collapse of molecular cores, potentially determining the final masses and rotation rates of newly forming stars. Within the nebula's complex structure, astronomers have identified numerous examples of stellar feedback processes. Stellar winds from young, massive stars create cavities in the surrounding molecular material, while their intense radiation pressure sculpts the nebula's edges and triggers star formation in compressed boundary layers. The result is a dynamic, evolving system where stellar birth and stellar feedback operate in complex interplay. The chemical composition of the North America Nebula reflects both its stellar population and its connection to the broader interstellar medium. The ionized regions show typical abundances for this part of our galaxy, while the molecular cores preserve more primitive compositions that provide insights into the initial conditions for star formation. Enhanced deuterium abundances in some molecular regions indicate material that has remained cold and unprocessed since the early universe. The North America Nebula's proximity and large angular size make it an ideal target for studying the detailed physics of massive star formation and stellar feedback. Ground-based telescopes can resolve structures smaller than 0.1 light-years across, allowing astronomers to trace the connections between large-scale ionization patterns and small-scale star formation sites. Chapter 12. The Sol Nebula, Heart of Stellar Creation. Our tranquil journey through the cosmos brings us to the Sol Nebula, designated IC 1848, located approximately 6,500 light-years away in the constellation Cassiopeia. This magnificent emission nebula, often paired with the nearby Heart Nebula, spans roughly 100 light-years across and represents one of the more distant stellar nurseries in our cosmic tour. As we approach this celestial sanctuary, I find myself wondering about the soul of your own cosmic journey. Are you perhaps listening from a place that holds special meaning for you? Maybe from the bedroom where you spent childhood nights dreaming of space travel, now in a city like Boston or Vienna. Or are you in a new location entirely, perhaps traveling through life and finding yourself tonight in Dubai or Sao Paulo, where the stars remind you that home is wherever you pause to contemplate the universe? Whatever location your life's journey has brought you to, and whatever hour your personal clock displays, consider how we are all connected through this shared cosmos that surrounds us. The Sol Nebula contains approximately 12,000 solar masses of material distributed across its complex structure. At its heart lies the open star cluster IC 1848, a group of hot, young stars that formed from the nebula's material roughly 1 to 2 million years ago. These stellar newborns, including several O-type giants with masses exceeding 20 solar masses, provide the intense ultraviolet radiation that ionizes the surrounding hydrogen and causes the nebula to glow in its characteristic red hue. Feel yourself drifting into this cosmic soul. The nebula's intricate structure reveals multiple generations of star formation, with older stellar populations having cleared out central cavities, while younger stars continue to form in the dense molecular material along the nebula's edges. This hierarchical process of stellar birth creates the complex network of bright emission regions, dark dust lanes, and elephant trunk structures that give the Solar Nebula its distinctive appearance. The Solar Nebula's chambers represent regions where different physical processes dominate the local environment. In the central cavity, hot ionized gas expands freely at temperatures around 10,000 Kelvin, creating a low-density bubble surrounded by denser, cooler material. Along the nebula's periphery, dense molecular cores maintain temperatures just a few degrees above absolute zero, providing ideal conditions for the slow gravitational collapse that leads to star formation. Stellar winds from the central massive stars play a crucial role in shaping the Solar Nebula's evolution. These winds, carrying material away from stellar surfaces at velocities exceeding 2,000 kilometers per second, interact with the surrounding medium to create complex shock structures and compression waves. The collision between stellar winds and dense molecular material often triggers new episodes of star formation in previously stable regions. The nebula's magnetic field structure influences both its appearance and its star formation efficiency. Invisible magnetic force lines, detectable through their effects on polarized starlight and radio emission, thread through the ionized gas and help organize the flow of charged particles. These magnetic fields may also play a role in supporting molecular cores against gravitational collapse, determining which regions will form stars and which will remain stable. As you float through this cosmic soul, observe how the nebula demonstrates the interconnected nature of stellar evolution and galactic ecology. The massive stars at the Solar Nebula's center will live only a few million years before ending their lives in supernova explosions. When that happens, they will distribute heavy elements throughout the local interstellar medium while also triggering new waves of star formation through their explosive shock waves. The chemical composition of different regions within the Solar Nebula provides insights into both stellar nucleosynthesis and interstellar chemistry. The central ionized regions show enhanced nitrogen abundances, indicating contamination from stellar winds that have processed hydrogen into heavier elements through nuclear burning. Meanwhile, the cold molecular cores preserve more primitive compositions that reflect the initial conditions present when the nebula first began forming stars. Within the Solar Nebula's structure, astronomers have identified numerous sites of active star formation using infrared and radio observations. Many of these stellar nurseries remain completely invisible to optical telescopes, hidden behind thick veils of dust that absorb and scatter visible light. However, the warm dust heated by embedded protostars glows brightly in infrared wavelengths, revealing the locations where new stars are taking their first steps toward nuclear ignition. The Solar Nebula's distance and structure make it an excellent laboratory for studying the physics of massive star formation in relative isolation from other major star-forming regions. Unlike more complex environments where multiple stellar associations interact, the Solar Nebula represents a relatively simple system where astronomers can trace clear cause and effect relationships between stellar feedback and ongoing star formation. The nebula's ongoing evolution will continue for millions of years as the central massive stars age and eventually explode as supernovae. These future explosions will completely transform the local environment, dispersing the remaining molecular material while enriching the interstellar medium with the products of stellar nucleosynthesis. In this way, today's stellar nursery will become tomorrow's supernova remnant, continuing the eternal cosmic cycle of stellar birth, life, and death. Chapter 13. The Pac-Man Nebula, Cosmic Appetite for Creation. Our gentle drift through the universe's stellar nurseries now brings us to the whimsically named Pac-Man Nebula, designated NGC 281, located approximately 9,500 light-years away in the constellation Cassiopeia. This emission nebula, spanning roughly 35 light-years across, derives its popular name from its resemblance to the classic video game character, complete with a distinctive mouth opening that appears to be consuming nearby dust clouds. Before we explore this cosmic arcade character, I'm curious about your own playful relationship with the cosmos. Are you perhaps observing from a location where you first fell in love with astronomy? Maybe from a childhood home in Phoenix or Manchester where patient parents once pointed out constellations on warm summer nights. Or are you discovering these celestial wonders for the first time, perhaps from a college dorm room in Mumbai or Sao Paulo where the pressures of studies give way to moments of cosmic contemplation? Whatever brought you to this moment of stargazing, and whatever hour your journey through the night has reached, remember that wonder and curiosity are the soul of all scientific discovery. The Pac-Man Nebula contains approximately 3,500 solar masses of material organized around the central star cluster IC 1590. This cluster of hot, young stars, dominated by several O-type giants, provides the intense ultraviolet radiation that ionizes the surrounding hydrogen and creates the nebula's characteristic red glow. The mouth of this cosmic Pac-Man results from a cavity carved out by stellar winds and radiation pressure from these central massive stars. Feel yourself drifting into this playful cosmic scene. The nebula's distinctive shape results from the complex interaction between stellar feedback and the three-dimensional structure of the original molecular cloud. Dense dust lanes create the mouth by blocking light from the nebula's far side, while bright emission regions trace areas where ionized hydrogen recombines and radiates energy back into space. The Pac-Man Nebula's central cavity demonstrates the powerful influence that massive stars exert on their birth environments. The O-type stars in cluster IC 1590 generate stellar winds with velocities exceeding 3,000 kilometers per second, carrying away approximately 1 Earth mass of material every million years. These high-velocity winds collide with the surrounding medium to create shock waves that heat gas to millions of degrees and carve out the observed cavity structure. Temperature gradients throughout the nebula create distinct ecological zones for different types of astrophysical processes. The central cavity maintains temperatures around 10,000 Kelvin in its ionized regions, while shock-heated material near the cavity walls can reach temperatures exceeding 100,000 Kelvin. In contrast, the dense molecular material that forms the nebula's body remains cold, with temperatures just 10 to 20 Kelvin above absolute zero. The nebula's magnetic field structure plays a crucial role in organizing its appearance and evolution. Magnetic force lines, invisible to optical observations but detectable through radio polarization measurements, thread through the ionized gas and help channel the flow of stellar winds. These magnetic fields may also influence the formation of the prominent dark globules visible along the nebula's edges, where future generations of stars are slowly taking shape. As you float through this cosmic gaming reference, observe how the Pac-Man Nebula demonstrates the triggering of star formation by massive stellar feedback. The compression waves generated by stellar winds and radiation pressure create dense regions in the surrounding molecular material where gravity can overcome thermal pressure and initiate collapse. Several of these triggered star formation sites are visible as bright-rimmed clouds along the nebula's periphery. The chemical composition of the Pac-Man Nebula reflects both the nucleosynthetic output of its central massive stars and the composition of the original molecular cloud. Enhanced nitrogen abundances in the central ionized regions indicate contamination from stellar winds that have processed hydrogen through the CNO cycle of nuclear burning. Meanwhile, the cold molecular regions preserve more primitive abundances that provide insights into galactic chemical evolution. Within the nebula's structure, infrared observations reveal numerous embedded young stellar objects that remain invisible to optical telescopes. These protostars, still surrounded by their natal dust cocoons, represent stars in various stages of formation. Some show evidence of bipolar outflows, jets of material expelled along the rotation axis of forming stars, that help remove angular momentum and allow continued accretion of material onto the central protostar. The Pac-Man Nebula's relatively simple structure and moderate distance make it an ideal laboratory for studying the physics of stellar feedback and triggered star formation. The clear cavity carved by the central star cluster provides a textbook example of how massive stars modify their birth environments, while the surrounding molecular material demonstrates various stages of the star formation process. The nebula's ongoing evolution will continue as the central massive stars age and eventually explode as supernovae. These future explosions will completely disrupt the current structure, dispersing the remaining molecular material while enriching the local interstellar medium with heavy elements forged in stellar cores. The shock waves from these explosions may also trigger new episodes of star formation in more distant molecular clouds, continuing the cosmic cycle of stellar birth and death across multiple generations. Epilogue: the eternal cosmic dance. As our gentle journey through the universe's stellar nurseries draws to a peaceful close, allow yourself to float in the serene darkness between the stars, contemplating the magnificent cosmic ballet we have witnessed together. From the familiar glow of the Orion Nebula to the distant majesty of the Sol Nebula, we have traveled across thousands of light years and millions of years of cosmic time. Let your breathing slow naturally as you consider the profound connections that link all these celestial nurseries. Each nebula we have visited represents a chapter in the ongoing story of cosmic evolution, a story that began 13.8 billion years ago with the Big Bang and continues today in the hearts of forming stars. The hydrogen glowing in these distant clouds was forged in the first few minutes after the universe began, while the heavier elements that create their intricate colors were manufactured in the nuclear furnaces of previous generations of stars. Feel yourself gently drifting in the cosmic ocean that connects all these stellar birthplaces. The interstellar medium through which we have traveled is not empty space, but rather a tenuous sea of gas and dust that extends throughout our galaxy. This medium carries the chemical signatures of billions of years of stellar evolution, mixing the ashes of dead stars with pristine material left over from the universe's youth. The nebulae we have explored tonight represent just a tiny fraction of the stellar nurseries operating throughout our Milky Way galaxy. At any given moment, thousands of similar regions are birthing new stars, each one a potential sun for future planetary systems. Some of these nascent stars may eventually host worlds where life develops and intelligence emerges, perhaps giving rise to beings who will one day gaze out at their own night sky and wonder about their place in the cosmic story. Consider the remarkable fact that you are intimately connected to all these distant stellar nurseries. The calcium in your bones was forged in the cores of massive stars and distributed through space by ancient supernova explosions. The iron in your blood was manufactured in stellar furnaces and delivered to the forming solar system 4.6 billion years ago. The oxygen you breathe was created by nuclear fusion in stars that lived and died before our sun was born. As you settle deeper into peaceful rest, carry with you the knowledge that star formation continues throughout the cosmos at this very moment. While you sleep, protostars are slowly heating up in the Eagle Nebula's pillars. Molecular clouds are collapsing under gravity's gentle influence in the Rosette Nebula, and stellar winds are sculpting new cavities in the North America Nebula. The universe never sleeps. It continues its ancient dance of creation and destruction, birth and death, on timescales that dwarf human experience but connect us all to the cosmic story. The colors of these cosmic nurseries: the deep reds of hydrogen, the blue-greens of oxygen, the yellows of sulfur, paint portraits of physics operating on scales beyond imagination. Each photon of light that eventually reaches our telescopes began its journey years, decades, or centuries ago in the heart of a glowing gas cloud. That light carries information about temperature, density, chemical composition, and magnetic fields across interstellar distances, allowing us to study these distant laboratories of stellar creation. In the gentle darkness of your resting place, whether you are in Mumbai or Montreal, Sao Paulo or Stockholm, Tokyo or Toronto, remember that you share the same night sky that has inspired humans for millennia. The same constellations that guided ancient navigators now frame these magnificent stellar nurseries for modern astronomers. The same cosmic processes that created the elements in your body continue to operate in nebulae scattered throughout our galaxy and beyond. Let your mind drift among these cosmic islands of creation, imagining the peaceful dance of gravity and gas that leads to stellar birth. Unlike the violent imagery often associated with space, the formation of stars is predominantly a gentle process. The slow compression of material over millions of years, the gradual heating of dense cores, the eventual ignition of nuclear fires that will burn for billions of years. It is a process of patience and persistence, operating on timescales that make mountains temporary and oceans ephemeral. The magnetic fields threading through these nebulae, invisible to our eyes but crucial to their structure, remind us that there are forces in the universe that operate beyond our everyday experience. These cosmic magnetic highways, extending across light years, guide the formation of stars and planets with an influence that is both subtle and profound. They connect regions separated by distances that would take light years to cross, creating a hidden architecture in the cosmos. As sleep approaches, carry with you the profound perspective that these stellar nurseries provide. Our Earth, our solar system, our entire human experience exists within the context of this vast cosmic ecosystem where stars are born, live, and die in cycles that span billions of years. We are not separate from this cosmic story. We are part of it, made from the same materials, governed by the same physical laws, participating in the same grand evolutionary process. The next generation of stars forming in the nebulae we have visited tonight will still be young when our sun has evolved into a red giant and eventually become a white dwarf. Some of these stellar newborns will outlive our sun by trillions of years, continuing to shine long after our solar system has become a memory preserved only in the expanding shells of a planetary nebula. In your dreams tonight, perhaps you will visit these cosmic nurseries again, floating peacefully among the glowing gas clouds where stars are born. You might drift through the towering pillars of the Eagle Nebula, feeling the slow compression of molecular material as gravity gathers the ingredients for new suns. Or you could find yourself in the heart of the Orion Nebula, watching as young, hot stars illuminate their birth environment with the light of nuclear fusion. Remember that astronomy is ultimately about connection, connecting us to the cosmos, to deep time, to physical processes operating on scales from the subatomic to the galactic. Every time you look up at the night sky, you are participating in the same activity that has driven human curiosity for thousands of years. You are connecting yourself to the cosmic story that links the formation of elements in stellar cores to the chemistry of life on Earth. The nebulae we have explored represent laboratories where the fundamental processes of physics and chemistry operate under extreme conditions impossible to replicate on Earth. In these cosmic furnaces, we can study matter and energy interacting across vast ranges of temperature, density, and magnetic field strength. They provide natural experiments in plasma physics, thermodynamics, and gravitational dynamics that expand our understanding of how the universe works. As you rest in the peaceful darkness, know that the cosmic dance continues. Stellar winds sculpt nebular boundaries, gravity compresses molecular cores, nuclear fusion ignites in stellar hearts, and the ancient cycle of stellar birth and death continues its eternal rhythm. You are part of this cosmic symphony, made from stellar ashes, living on a planet warmed by nuclear fusion, breathing oxygen created in the cores of massive stars that died before our solar system formed. The beauty of these stellar nurseries lies not just in their visual splendor, but in what they represent. The ongoing creativity of the cosmos, the persistence of physical processes across unimaginable scales of space and time, and the deep connections that link every atom in your body to the nuclear furnaces of distant stars. In studying these nebulae, we study ourselves and our place in the grand cosmic story. Rest peacefully now, knowing that you are connected to these magnificent stellar birthplaces by bonds deeper than gravity and stronger than time. The same physical laws that govern the collapse of molecular clouds also govern the beating of your heart. The same nuclear processes that light up distant nebulae also power the sun that warms your world. The same chemical elements that create the beautiful colors of emission nebulae also flow through your bloodstream and spark the neurons in your brain. Sweet dreams, fellow traveler of the cosmos. May your sleep be filled with visions of glowing gas clouds and newborn stars, of cosmic pillars reaching across light years and stellar winds painting celestial masterpieces. And when you wake, remember that you have journeyed to the very hearts of creation itself, witnessing the processes that make stars, planets, and ultimately, life possible throughout the universe. The nebulae will continue their ancient dance while you rest, slowly spinning out new chapters in the cosmic story that began billions of years ago and will continue for billions more. You are part of that story, made of star stuff, animated by stellar energy, contemplating the cosmos from which you came and to which you will someday return. Sleep well under the same stars that shine down on stellar nurseries scattered across our galaxy, and dream of the cosmic wonders that connect us all in the infinite tapestry of space and time.